So, okay, I think we can start now. Welcome to all of you to our ET2SMEs kickoff meeting. ET2SMEs stands for Maximizing the Economic and Social Impact of the Implementation of the Einstein Telescope in the Euregio Meuse-Rhine. And first of all, I would like to give you a short overview over our agenda. We will start with the welcome speeches from Dr. Tim Grüttemeier, District Administrator of the City Region Aachen, and Mark Voss. He's the coordinator Interreg Euregio Meuse-Rhine. Then Professor Dr. Stefan Hild from the University of Maastricht and NICEF will give us an insight into the Einstein Telescope and the research activities for a soft landing in the Dutch-Belgian-German cross-border region. And after that, we will have two shorter presentations. The first one is ET2SMEs, the Einstein Telescope and SMEs in a nutshell, targets, offers, and added values for SMEs by Ralf Meyer from the Leadpartner AGIT. And then we have the first results of the online catalog, which is already running. There's a questionnaire on our website. It's an online catalog of ET technologies, and the mapping, this is the questionnaire I mentioned, of the ET competencies in the extended Euregio Meuse-Rhine by Annick Pierrard and Geoffrey Parks. In the second part of our meeting, after a short break, we will have two parallel sessions, but at 2:00 p.m. I will post the links of these sessions again in our chat. The first session is about the technologies led by Professor Dr. Achim Stahl from the RWTH Aachen. And the second one is the geology technologies by Professor Dr. Frédéric Nguyen from the University of Liège. In each session, we have 15 minutes of input, and then we have 15 minutes of question and answer, a small discussion about this. And I hope so. I think at 2:30 we will be finished. But first of all, our welcome. We will start with Dr. Tim Grüttemeier, the District Administrator of the City Region Aachen in Germany. So I stop my presentation, and Dr. Grüttemeier, the stage is yours.
Yeah, thank you so much, dear Mr. Köster, dear Mr. Voss, dear professors from the participating universities, dear partners from the border triangle, dear entrepreneurs, dear participants. I would like to warmly welcome you to the digital kickoff event of the Interreg project ET2SMEs. I must confess that there are certainly abbreviations that roll off the tongue more easily. I am particularly pleased that we have again managed to initiate another Interreg project in the Euregio Meuse-Rhine. ET2SMEs stands for Maximizing Economic Impact of the Einstein Telescope to small and medium-sized enterprises in the greater Euregio Meuse-Rhine area, and clearly shows what is important in the project: to link the technological potential that results from the Einstein Telescope to the Euregional economy. The Einstein Telescope offers us the unique opportunity to bring the EMR to the forefront of gravitational wave research. It is therefore a matter of personal concern to me that the telescope comes to our Euregio Meuse-Rhine. Over the past few months, by means of dialogues with the responsible State Secretary, Mr. Thomas Rachel, and a letter to the Federal Ministry of Education and Research, I have campaigned for the necessary support for the application process on the German side. In its meeting on March the 19th, the County Council also spoke out in favor of the Einstein Telescope across all political groups. In addition to this lobbying works for the Einstein Telescope, the StädteRegion Aachen will also support the project financially. That is why we are providing 50,000 euros that can be used for necessary preparatory work. In view of the total cost of the project, it is certainly only a drop in the bucket, but it was and is important to us to also document in this way we are committing to this project. Getting the contract awarded to the Einstein Telescope is one thing. Using the technological and economic potential of the Einstein Telescope in the Euregio is another. And at this point, I'm convinced that as a technology region, with the potential of our universities, our technology-oriented entrepreneurs, and our innovative minds in the region, we recreate an ecosystem around the Einstein Telescope as part of this project, and thus provide new impetus for cross-border cooperation. We have to be able to involve all stakeholders to award contracts in the region and to allow medium-sized companies to participate in the project. Furthermore, we have the opportunity to generate added value through the Einstein Telescope. We are at the beginning of a pioneering structural change process in which new digital and sustainable technologies are to be established in our region. At the same time, there are opportunities to generate new fields of research, bring new ideas to the region, and promote its successfully structural development. In addition, the project offers the opportunity to bring more scientifically skilled people to the Euregio, and at the same time introduce the residents to the highly exciting topics of gravitational research. I'm convinced that we will benefit in the Euregio Meuse-Rhine from the Einstein Telescope, and I wish all those involved every success for the project, an exciting and informative event for those present, and good conversations on the sidelines and in the chat. Thanks for your attention.
Thank you very much. And now I give the floor to Mark Voss. He's the coordinator of the Interreg Euregio Meuse-Rhine. So here is your presentation.
So thank you, and excuse me again for the bad connection in the beginning. So I'm happy to speak to you, to all of you, for the third Interreg project and the Einstein Telescope history or story. We are happy with your project because it's a large investment in the Einstein Telescope, and this project, ET2SMEs, will guide SMEs in how to benefit from the implementation of this Einstein Telescope. So very happy with your project, and I want to thank everyone who is joining in this project. We have 7 project partners who collaborate across borders in this project. Thanks to all of you, and a special thank to AGIT, who is the lead partner in this project. We hope you will have a fruitful project with a lot of good results. We are looking forward to see all those results. Also, a great thank to our 13 partners who support this project, who finance or co-finance this project also. A special thank to our project manager, Anka Simeon, who collaborated also in this assistance, and also our regional contact point, Stefan Bars from Regio Aachen. Thank to both colleagues to assist in this project. For the participants, we support this project with 1 million ERDF approximately. Now, what is the European funding? Perhaps the next slide. Yeah, Interreg is one of the key instruments for the European Union to support cooperation across borders through funding, through project funding, and the aim is to tackle joint and common challenges and find shared solutions in the fields such as health, environment, innovation, research, education, transport, and in your case, it's exactly innovation what we are financing. Last year, we celebrated the 30 years of Interreg history, the cooperation across borders to foster European cohesion. Europe made it possible for people to travel freely across borders, but we still see that there have been a lot of issues when we cross borders. Also, when you live in the border region, we see still some obstacles, and the Interreg funding is meant to tackle those challenges. Perhaps the next slide. What is our position in the entire world of the European funding? We are one of all those Interreg programs and the European Commission. They foresaw in the actual program period 2014-2020 10 billion ERDF funding. There they finance more than 100 Interreg programs, and we are one of the 60 cross-border programs within the Interreg world. So we have a lot of colleague programs, but we in the Euregio Meuse-Rhine, we are one of the oldest. We exist from the beginning, already 30 years. Perhaps the next slide. Why do we cooperate and why it's so important? Why is Europe invest so much money in their cohesion policy? Because we and the European Commission believe in sharing ideas, know-how, and learning from each other. And in order to grow together, we have to find shared solutions for common problems. And this project, ET2SMEs, and also the two other project for the Einstein Telescope shows how it works together as one project and as one regio across borders. So thank you very much for that. Perhaps the next slide. What have we done in this period, existing period? Because we are at the end of the existing period, we will start a new program, hopefully beginning next year. At this moment, we had 6 calls plus a special COVID call. In the meantime, we selected 62 projects. We worked together with more than 300 project partners, and in total, there is an investment of 196 million for project cost, out of which we finance with European means, ERDF means, 50%, so almost 100 million in this region. Perhaps the next slide. And how is it divided? Yeah, we worked on 4 axes, 4 themes: innovation, economy 2020, the social inclusion and territorial development, and our own financing the technical assistance to manage the entire program. Next slide, please. What will we do in the future? As I already announced, we are working on the new program right now. We are working together with our 13 partners to end up with a new program by the end of this year, hopefully approved by the European Commission. What do we want to do? Our teams in the new program are, perhaps next slide. We want to work around industrial transition, then towards a greener society. We want to work on healthier citizens, very important in this COVID period, but also tourism in a high quality region, and how can we live and work without borders in the cross-border region. And these are the grand societal challenges we selected with our 13 partners, but also after consulting some public authorities and also the public in general, and during some public events last year and already in 2019. Perhaps next slide. Where are we now? So we are finalizing the program right now, and we hope we can hand in an official document around September to start with the new program in 2022. And then we have new means, new facilities to select new projects in future. At this moment, we are also launching a last call, the eighth call in the actual program, because we had some budget left. Around 5 million ERDF is still left in this program period. We will launch today or tomorrow the latest call, and this is the 8th call for this program. So if you have ideas, please look at our website to see what we will finance in this call. Perhaps the next slide. Why is it so important to have ET2SMEs in our program? because we believe in the strong partnerships who is involved in this project. We have very competent project partners. It's a very innovative project. We are working across borders. This cooperation is very well explained in this project. There is a close cooperation with the two other Einstein projects in Interreg. Was already named in the previous presentation. And you are also looking to SMEs, which is very important to have some SMEs in our program, that we can work together with SMEs to see what's working across border between all those SMEs. So we are looking forward to see your results, and we wish you all the luck with this very exciting third project in the Einstein Telescope history. And perhaps the last slide, to our partners. I always want to thank all our 13 partners. They are here on the screen. So thank you all those partners for the cooperation and the co-financing in this project. And if you want to find something about us, you can look at our social media, which is shown here in this slide. So thank you very much for your attention. I wish you all the luck. I wish you a lot of good cooperation between SMEs, and we are looking forward to visit the Einstein Telescope in a few years. Thank you very much.
Thank you very much, Mark Voss, for your introduction. And now I can hand over the remote to Professor Dr. Stefan Hild.
Hello, good afternoon. Good. Okay, yeah. Thank you very much for the opportunity to talk here at such a nice occasion. We were discussing ET2SME for a long time, and it's really nice to see this coming reality. And I will take the opportunity to talk a little bit about the scientific background. You know, what is it? Why are we so excited about the Einstein Telescope? What is the scale and the time scales? And then what are we doing right now already to prepare for the Einstein Telescope? Next slide, please.
Okay.
So the story really starts more than 100 years ago with Albert Einstein inventing general relativity. And one of the tiny details of his theory was that there was gravitational waves coming out, which is a phenomenon that he thought would be not really relevant for us because they are such a small effect of very heavy objects rippling and curving and bending the fabric of space-time. 100 years later, with lots and lots of technology development, you know, lasers, getting precision measurements much, much better, actually we were able, a collaboration of about 1,000 people, were able to first show that these gravitational waves exist. And there was a discovery of two black holes colliding 1.4 billion years ago. And then these waves were sent out and racing towards us to be picked up by our detectors in 2016. And that has started really a complete new epoch, I think, in astronomy that was rewarded with the Nobel Prize in 2017. But it's really more about this kind of opening a completely new window to the universe. So far, nearly everything we know about the cosmos is really kind of from observing electromagnetic radiation coming in, light and other parts. And here we have now something where we can actually open up the window to the dark side of the universe, really kind of black holes, and really understanding also what are the constituents of our universe and what drives it. I mean, many of you will have heard that only 5% of the universe really exists of things like you and me and the things around us, atoms and electrons, and 95% are dark matter and dark energy. And I don't want to go into detail what they are, but really kind of, we hope the Einstein Telescope will play its game and it contribute to shedding some light on this and giving us the understanding of these very, very big questions. Okay, so this is kind of the science part, and I stop here with the science. So what does it look like, the Einstein Telescope? If we go to the next slide, please. Okay, so on the left-hand side, you see these marvelous machines which exist right now, which we have discovered gravitational waves. They can measure length distances over kilometer scale to this mind-boggling thousands or 10,000s of a proton diameter. So 0.000, and you put in 18 zeros and then 1 meters. But this is actually not good enough, and we think we can do it better. And that is really kind of that we say, okay, these facilities will come to the end of their lifetime and we need something new. And that is the Einstein Telescope. And you see here what we envisage it to look like on the right-hand side. And as I said, for us, it's a big discovery machine with which we will see kind of black holes and neutron stars throughout the universe colliding, learning about them, and maybe even looking back towards the Big Bang, much, much further down, much closer to the real Big Bang than what would be possible with other types of astronomy. So how does Einstein look like? If you go to the next slide, we can take you on a tour. If you start the video, so if in 10, 15 years or so, you come to the region, hopefully we can give you a tour of what you see here in an animation. In reality, we have this big triangular underground structure, 10 by 10 kilometers. You see here lots of caverns, lots of engineering, kind of geology, underground construction. You see here essential parts, the vacuum system, quite a lot of high-tech installations for the mirrors, for the actuators. You see different systems here. Some are warm, some are at cryogenic temperatures to get us to this marvelous sensitivity here. Okay, I think we can put a link to the video offline and then people can have a look at this. Here it's now zooming out. You see one of these corner stations and then all of this will be underground. So obviously on the surface, everything will be pristine and hopefully people will not see much of what is actually underground there. And hopefully with that, we can observe for the most part of the 21st century gravitational waves. Good, so this is what we want to do. How are we getting there? If you go to the next slide, you see the dimensions of the Einstein Telescope are quite huge, huge in meters, but also huge in costs. So there's a certain challenge there. But as we all know, challenges you can also see as an opportunity. So we have here, if you look at the left-hand side, the construction cost of the Einstein Telescope of 1.9 billion euros. Which is quite a lot of money, and that actually poses a challenge. But we think it's money well invested. Various studies out there, and I mean, I just put it here in the red box. From what we think and what these studies have found is that for every euro that we invest in the Einstein Telescope, we think we get a total output of 3.6 euros actually back. So it's a worthwhile thing. And the other thing you see here on these numbers is obviously this is not something that scientists can do on their own. This is really kind of the large infrastructure and so on is really something where industry has to take the leading role in building this, putting this together, making sure the quality control is right and so on. So this is really why we are so keen to have things like ET2SME to really get this connection developed further and have a head start there. If you go to the next slide, we put here a simplified timeline. So where are we in the Einstein Telescope? We applied last year to the so-called European Research Infrastructure Roadmap. We will get a decision over the next few months whether this will be accepted. And then the next steps are that there are two different site proposals at the moment on the table. One is our region. The competition is on Sardinia in Italy. And we believe that in 2025, there will be a decision and then construction can actually start. And then in 2034, 2035, as I said, I hope we can all go underground and see the things we saw in the video in real life. So this really is the time frame, the bigger frame for the costs, but also the time frame in which we are dealing with. Okay, and what you have heard already quite a lot is that, coming back to the soft landing, that we are preparing for the Einstein Telescope. So we are not waiting for the site decision, but actually we're doing our homework to qualify the site here to develop technology. And the two projects which were supported or are supported by Interreg, and we are very grateful to have these two, are eTest and ET Pathfinder. And I would like to spend a few minutes on each of these, just explaining what we are doing in there. So if you go to the next slide. Very busy slide, don't need to look at all of the text here. It's really kind of to give you an impression of what we want to build here. ET Pathfinder is trying to build an Einstein Telescope. Instead of with 10 kilometers long arms, you take most of the vacuum tube in between out, make it just 10 or 20 meters long, and then try to show various technologies around the mirrors, around cooling, around the optics and so on in a shorter time, in a smaller setting. It's a 15 million euro project with 15, started off with 15 partners. We're now 16 partners. We added France in there. And we're currently discussing also with other countries and institutions to join in here. And if you would come to the place where the ET Pathfinder will be built, then you see a picture at the lower right. This is what happens if you would walk into the Domain 30 in Maastricht. That's a purpose-built clean room where the ET Pathfinder will be built. Next slide. Just to give you a little bit of an understanding of the timeline for ET Pathfinder. ET Pathfinder is thought to be a long-term technology development. So to a certain extent, it's also independent of, in the end, a site decision. Obviously, we have very strong hopes that the site decision will go in our favor, but it will allow us to do technology development really kind of for the next few decades, taking into account that the Einstein Telescope will operate from 2035 to 2085. So that means there will be lots of different technologies coming online. If you think about what technologies, how much change there is in 50 years, if you now go back 50 years and think about what technologies were around, that's quite a big change. So every now and then you need to update these technologies. And this is what we try to develop in parallel to the Einstein Telescope. And on the next slide, I just put a little bit of what are the current activities right now here, really just to give you a flavor. So it's really kind of covering most parts that you would need also for the interferometry, for the optics, for the vacuum system and cryogenics and so on, what you need for the Einstein Telescope. And you see here, this becomes slowly reality. In the upper left, there's the first mirror suspensions where we run tests. In the middle, you see one of my colleagues actually holding the first silicon mirror blank in there. And then on the lower right, you see a vacuum system as it is currently in production. In the lower left, you get the feeling for the dimension. This is one of the structures which goes around one of these towers. And this is tested currently in Antwerp. So quite a lot of things going on. And this is kind of marching forward. Good. So that's ET Pathfinder. The test from Interreg EMR, I should say, ET Pathfinder was Interreg Flanders, Netherlands, is a similar scale. It's 15 million euros. Again, 10 to 15 partners involved. There's some overlap in the institutions there. And the nice thing about eTest is that it has two different components, very distinct components. One is to build a prototype for large suspended cryogenic silicon mirror. So really kind of in contrast to ET Pathfinder, where you saw we go for small mirrors. In eTest, it should really be one very, very big mirror cooled down with very innovative technology. And then on the other part, eTest allows us to look into the geology, into the underground engineering, developing noise models and really kind of understanding the soil properties, the noise levels in our region here to show that the region is really well optimized and suitable for building the Einstein Telescope here. If you go to the next slide. So here you see some of the aspects of the cold mirror prototype. And you see here on the left-hand side, there will be at CSL in Liège, there will be a very nice prototype facility in a big vacuum chamber, testing the cooling of one of these big mirrors in combination with the seismic isolation, reducing the seismic noise by many, many orders of magnitude. And coupled to this is lots of optical component development, talking about better coatings, kind of the surfaces of our mirrors, lasers, and photodetectors. So all of the whole train of photonics that you need to build laser interferometers. And then the second part, here you see some impressions of what's happening on the geology side. As I said, people are planting lots and lots of surface sensors, shake the ground on purpose or use earthquakes or other excitations to actually first understand the noise level, which is very important for the Einstein Telescope. Okay, so if you go to the, so that was an overview of ET Pathfinder and eTest, and now we can make the closer circle and go to how this relates to ET2SME. So we have two projects, and obviously these projects combines one unique goal, and that is really kind of to get ET into the EMR region. There's a very clear timeline now. We know how to engage, what we need to do, and there's obviously a big effort between scientists and, as I said, I mean, it's absolutely essential to get industry on board, help us with all of these things. There's a huge opportunity for this, and many of you from the names I saw on the chat have engaged in the past with our industrial advisory board. So if you go to the next slide, with all of this in mind, now is really the nice time. Now we have ET2SME. You will hear much more about this. And with that, as I think we close the circle of these projects and really, I think, have a fabulous foundation for our future work on the Einstein Telescope. Thank you very much for your attention.
Yeah, thank you very much. And we will go on with Ralf Meyer.
Yeah, maybe I can already say some words of welcome in the meantime. So a warm welcome also from our side, from AGIT, as already mentioned, the lead partner of ET2SMEs project. We are very happy to have you here in this meeting today. Thank you for the overwhelming resonance, I have to say, for this project and for this meeting. We have round about or more than 200 registrations and more than 100 businesses interested in these activities we have here. If you could click through the presentation, Hendrik, it would be nice. Well, I would directly, if you go to the next slide, I would directly continue to the speech of Stefan Hild. So you already are aware of the existing two cross-border projects. We have to see that the cross-border region and also the regions itself, that they are doing a lot of preparations for a soft landing of this Einstein Telescope here in our region. So the process is fully running, and we have already investments, not the ones you can see here, but in total of 45 million euro that are invested to bring this telescope here. Well, ET2SMEs, if you click once more, it is the third project that was already mentioned. What do we do in a nutshell? We want to promote the cooperation between SMEs, but also large companies and R&D institutions that deal with the Einstein Telescope technologies in a broad understanding. And what this especially does mean, I will come back to this question later, and especially towards multiple application fields. And we want to do this by initiating SME-driven cross-border R&D projects. The relation between the three projects, if you go to the next slide, please, is very close. So we have not a standalone situation, but we have three projects working together. You see this here. You see the partners all over the different regions that are participating, and I can really say that we have a very strong network supporting each other in this target of having this telescope here in this region. The next slide, please. First of all, we have to understand what are the technologies behind the Einstein Telescope. The key enabling technologies, we have 6 of them, and the Einstein Telescope is addressing at least 5 of these key enabling technologies, which are most relevant for future economic and technology development in Europe, but also worldwide. And if you click once more, you can see that we have a large range of instrument technologies that the Einstein Telescope is addressing. We have also the geology technologies. Please show also these technologies. Yeah, so you can see them in red here. So we have a broad range already of technologies that are addressed. And if you click several times more, you can see what the basic idea is, that we want to enable these technologies with a great impact on various application fields. That means for the astronomy as such, of course, but we are thinking further. We are thinking on aerospace, we are thinking on automotive, but we are thinking also on further high demanding application fields where these new technology developments may be useful for. The next slide, please. So in a nutshell, you can see here in one picture what we are doing within the ET2SMEs project. At the bottom, you can see that we want to establish, first of all, an active business development support. That means we want to map technologies, we want to map competencies that are available here in the enlarged cross-border region. We do this via company visits, we do this especially also by networking events and consortia building activities. So bringing together the right and complementary partners across borders. That is what we do first. And second is that we really provide attractive fundings for establishing these research and development projects across borders. And finally, also to sustain activities. I will come back to that, what this means later on. To the next slide. So what are the added values? Because that's most interesting for the businesses, for the SMEs. Why should you join? First of all, looking at the mapping, you can enhance your visibility. You can contribute with your expertise in the technologies on a new online mapping platform. We will show you later. Annick and Geoffrey will do this, explain you a little bit more about this process, how we do it. And by being on this online mapping platform for ET, this will help you to gain international recognition with your services, with your products. Second, we are talking about cross-border, and so it is very important that we also see the huge opportunity to expand your network. You can improve your business and R&D contacts across borders, and you can establish one-to-one contacts to interesting complementary partners. We do this via business development support, as I showed you already before. We do company visits to understand what your business model is. We do events and partnering workshops in order to bring the right complementary partners together. And we give you a really one-to-one personal support in helping you building the right consortia. Next one. The third and maybe most interesting part is that we provide attractive fundings in setting up innovation R&D projects with other regional SMEs. We provide innovation vouchers with amounts between 25 and 50,000 euro. Well, you see here some of the cornerstones. We think on innovation projects that run up to 9 months. At least there have to be 2 SMEs from the extended EMR working together across borders. Other partners, large businesses, research institutions, of course, can join. You have to match the funding you receive with the same amount of own contributions. And currently, the further details of this voucher scheme are worked out. So we are quite sure that we will be able to provide you with further details in summer. And you can find all the preconditions for receiving the vouchers then also on our website. The next one. Well, I talked about sustainability. it's also an added value for you that you can join an Einstein Telescope community. We want to set up, or we have already set up, I have to say, the Einstein Telescope Industrial Advisory Board. It will be a continuing exchange and advice platform between business and research. And yeah, as we are talking about a process of 10, 12 and more years until the Einstein Telescope will be established here, it will be an activity, an ongoing activity for the next year. So you also have the opportunity to join this advisory board. So these are four clear added values in how also SMEs can profit from the Einstein Telescope and how they can profit already in 2021 from this huge facility. The next one. Well, these are our partners within the ET2SMEs project. It was already mentioned. We have 7 full partners, but we have also 5 associated partners, and we have letters of intent partners who are supporting us. We are very glad to have this support, which is also including partners from neighboring regions. We really have to think in a broader sense of developing this new facility. Next one. Thank you very much for your attention. And now I will pass over to Annick and to Geoffrey, and they will explain you how the very first results were achieved within the project and what and how the mapping procedure looks like. Thank you very much.
Thank you, Ralf. Thanks a lot. So I'm Annick Pierrard. I'm senior manager at the Interface Entreprise University of Liège, and I am also the e-test coordinator. So I had the pleasure to welcome you, if you remember well, to our first joint industrial advisory board. It was the 10th of December. And at that moment, I was crossing my fingers, and you see, it worked. And we are here with the new ET2SME project. And I'm super happy to already show you the first communication achievements, because we created the website, Hendrik, so you can go to the next slide. Yeah. And what's important for you to know is that you can really follow us on a different, via different ways, LinkedIn, Instagram, and also Twitter. And we don't have a group for ET2SME, but we are publishing from our own profile. So in the chat, I've written my address. Don't hesitate to connect should you have any question about e-test, ET2SMEs, and don't hesitate to connect to my partners, because we can help you in function of the region you are localized. And of course, the other things we have achieved is the website, and it's really not a landing page. You will see that after 3 months, we started this project on the right foot. So Hendrik, maybe you can go quickly on the website. And I will show you, because there are already a lot of important information you can find.
Can you see the website or still the PowerPoint?
No, we see the website. Okay. And then if you just click on ET Technologies, we'll just show the different, you will have an access to the ET Technology Online Catalogue that I will show just after. And also, Hendrik, if you just click on...
You can also steering, you have control over my mouse, but okay.
I have control?
Yeah, you have.
Oh, okay, I'm in control now. So, and here you have this access, you know, to the Joint Industrial Advisory Board. And I wanted to stress that we gave, we paid a lot of attention in communication and collaboration and linked between the project, because we want you to have the complete overview, you know, of the complete ecosystem. So if you click here and if you want to participate to the joint industrial advisory board, this will connect you with my e-test website, and there you have this online form where from now on, if it's not done yet, you can register and you can be part of our industrial advisory board. So you are here, you see, the projects are completely interlinked. I am coordinating e-test, and my role in this project too is really to have this project working together and really being connected as much as possible. So when you go back to the ET2SME, you see that you will have already a lot of information about the mapping, because we have launched a survey, and Geoffrey will talk a lot about it. He will explain you how important it is to participate to our survey. You will have very soon information about our vouchers. We are already publishing a lot of news. Here you will find a lot of publication, videos, articles, events we are organizing. And one also very important things, you have the contact details of all the partners. You see, don't hesitate to contact us per region, or well, the per people you know, you just ask information and we will guide you. Okay, so then the next achievement, so if we go to the next slide, is the ET, yes, it is the online catalog of ET technology, because this was our homework since the last industrial advisory board. If you remember well, we promised you, maybe on the next slide, Hendrik. Yeah, we promised you to build the online catalog of the ET technology. And so we started. This is an ongoing process. Please don't consider that this is the final version of it. This is the first version of it. And you will see that you will have access to 8 technologies for the instrument part, and already to 4 fields of technology for the geology side. And here you will find the way we have built our technology sheets. So if I'm clicking on it, I'm on the ET2SME website, I go down, and for instance, I will show you the cryogenics technology sheet. So what the industry must really focus on is here the key challenge in the nutshell. This is what we need. This is what is expected in terms of innovation, in terms of expertise. Then you have, of course, the short description of what is cryogenics, the state of the art of cryogenics in existing gravitational wave detectors, and also the TRL when we have it. Then the intended use in the frame of the Einstein Telescope, but also, of course, the improvement needed. And this is for the companies, well, I would say the most important things to focus on. And then also, we don't want to limit ourselves, you know, to the Einstein Telescope. We want you to develop innovation that can also be used in other application. And here we present you also some other possible application. And we remain really open to all of you. You also have a role to play in the writing of our catalog. Here you have the related project and labs where we are using this technology, and then the ongoing and future procurements. Always remember, we are publishing all the procurements via the legal channel, but also on the e-test website. Remember, you have this sheet with all the procurements that are published and that are done during the e-test project. Then to help you, if you are a company, you have here the name of the 5 business developers that you really should contact if you can collaborate with us in this technology. And they will do the link with the technology contact, who is the scientist, who really is the specialist in this technology and wrote the major part of this sheet. But please contact the business developer first. He will put you through the right person. So I think we did a great job. because you will see all the catalog is now online. You have something that you should really read and go and visit and identify and see where you are fitting. And just to show you that we've really done the same for the geology, you have 4 fields of activity, and there you have the separate technology sheets for the geology sites. So I think I will stop here and I will give the floor to Geoffrey because we don't have a lot of time. And Geoffrey will present you the survey. Geoffrey?
Yes, I'm just waiting for the slide.
Okay, Annick, can you?
That's already done. Geoffrey, you can you are in control of the mouse.
Ah, okay.
And
okay.
yeah,
okay.
So you can go ahead.
So thank you, Annick. My name is Geoffrey Parks. Hi, everybody. I'm working in the innovation department of Sowalfin. I'm in charge of the craft platform mapping tool, and therefore Sowalfin is fully associated in this project, mainly for the realization of the online survey and the mapping of companies. So within the framework of this working package mapping, I'm going to talk to you about those 2 items which are currently occupying us, namely the online form and the mapping. So the objective is therefore to explain you what they consist of and what is the goal within the framework of this great project. And last but not least, to give you the good reasons to be part of it. So to begin with, regarding this online survey, a few points to summarize how and why this online survey. So mainly is to collect expression of interest from companies, but as well as research centers from your companies for these projects, is to get online survey accessible throughout the project and easy to complete. It will be on the website. I will explain that. Of course, it's compliant with the GDPR, but mainly this survey will make it possible to get a first contact with you, to know your company, to inform you about the technologies targeted in this ET2SMEs project, and of course for the working package too, to prepare visits for your companies and to know you previously before a first contact. And finally, to establish a mapping that will build some bridge between companies and to build some partnerships and possible collaboration beyond borders. So we have the results of this survey in the central file, and we decided to send to all the partners twice a week the result of the survey to just to follow the evolution of the companies involved in this project. Okay, so as I said, this online form is accessible on the project website and will remain so throughout the project if other actors want to register in this project afterwards. So from today, please feel free to browse the website, to read carefully the online catalog of technologies, and if you are interested, to fill in the form, complete it as much as possible to get the most information for you and to get really an international visibility. And on the right, you've got an example, first general information that we ask for this questionnaire to identify your company. So at the start of the questionnaire, after 2 or 3 questions for identifying your company, we leave 3 possible choices. Either to continue to filling out the questionnaire, either to stop if you are not interested in, or Third choice, to be contacted directly by a phone call from one of our partners for more information before coming back to the questionnaire. So if you feel that you need more information to fill in the questionnaire, please feel free to ask to be called in this survey. So briefly, here are some results. I won't go into details about the figures, but the result obtained from the survey updated, it was on Tuesday. So as you can see, we have in particular the number of questionnaires completed or not in each partner region, but also in the extended EMR, then sorted by country. And we also have the number of actors who wish to be contacted by phone. So it's a way, it's a dashboard for us to be sure to call you back if you need more information. More interestingly, we can already collect statistics on the main technologies where the players where you could have expressed an interest, in which sectors you are positioning yourself, and the kind of organization represented. So it helps us to check the most solicited technologies and to prepare the visits and to think about building those bridges between different actors. So about the mapping now, as explained, the data collected will also be used to map the actors potentially involved in this project and to give you international visibility. So the realization is in progress of this mapping, but I will show you already what this could bring together in the next slide. But the two deliverables that we want to obtain are, on the one hand, a SWOT analysis in order to highlight the strengths and weaknesses of this value chain and the actors who compose it, and on the other hand, to constitute some clusters in the different technologies. So in practice, here's what this mapping will give concretely with the craft tool. We'll go browsing on the mapping. Okay, so here you can see on one hand we have a directory listing the companies and players in each region. Here we have the different technologies that you could be involved in. For example, instruments. If I select vacuum, you can see the updated list of those companies implied in vacuum. And if you need it, you can get some details about the company. It's really important for us because it's for your visibility. And if you need to look for a potential partner, it's the good way to find it. You've got also the mapping. You can couple with different filter, like the instrument, but also the regional filter. You've got keywords for the research motor. So all is done to select and to find the good company you want to work with or you need to know. So just close that. Okay. No, sorry. Okay, and so here is what we want to achieve at the final goal for this mapping is a 3D model of the telescope using craft technology. So each time the mouse passes over one of the targeted technologies, here for example instrument lasers, it will appear and will return either to the information in the online catalog technologies on the website or to the list of reference companies with the possibility of having information on one or another business on your business, for example. So it's really a visually strong tool. We're proud of this project to be carried out, and it's really a good way, a good opportunity for you for international visibility and to create some partnerships with potential other players. Thank you for your attention.
Yeah, maybe some final remarks about the fundings, but I think that was already mentioned. So ET2SMEs will be financed via the RADF funds. You can see the amounts here. Please, next slide. You can see the financiers, and you can see finally all the partners, active full partners within this project. So thank you very much for your attention. I think we have now reached the end of the first part of the event. Thank you very much for joining, and now we will step over to the second part, and I will give the floor back to Hendrik.
Thank you very much. I will copy the links into the chat. So if you want to join the first session, which is about the instrument technologies, just stay in this meeting. And if you want to join the the geology session, by Frédéric Nguyen, then use the link to change to the other session. So, and from my side, thank you very much for your attention. I don't know if we meet again afterwards, because afterwards we won't meet again. So yes, I think we will have about 5-minute breaks, 5-minute breaks, so that you have enough time to change the session as you like. Thank you. So welcome to the first session. It's about the instruments, as already announced, and we will have first we will have a presentation by Professor Dr. Achim Stahl from the RWTH Aachen, and afterwards we have about 15 minutes, or how much it takes, to answer your questions and get into a short discussion. So, Professor Dr. Achim Stahl, the stage is yours, the screen.
Thank you. Welcome to the second part. So it's a pleasure for me to talk to you about the technologies of the Einstein Telescope. But let me first introduce myself. My name is Achim Stahl. I'm a professor of experimental physics at the RWTH Aachen University. And I'm working in developing instruments for basic research experiments. And since a few years, I'm now doing this for the Einstein Telescope. Let me start with my one-slide introduction on how a gravitational wave detector works. If a gravitational wave, after traveling for millions of years through the universe, finally reaches the Earth, it deforms periodically the space-time in which the Earth is embedded, and it looks a bit like the Earth starts wobbling, as you can see in the bottom right of the picture. So all we have to do is we have to put a very precise ruler on the Earth, and the ruler will change its length along with the gravitational wave. And that's what we're actually doing. And we're using a well-known precise instrument. This is the Michelson interferometer to measure the length of its arms and the length of its arms. This is a ruler. So when the gravitational wave comes, then also the interferometer will start wobbling. And due to the phase shifts, we will see periodic changes in intensity on the output of the interferometer. And this is actually what we measure, and from which we then learn all about the science of the origin of this gravitational wave. What's important here is the scale. Of course, this picture that you see here is largely exaggerated. The deformations are minuscule. And to give you an idea, what you see here is the absolute change of the length of such an arm in micrometers. Now, it's an incredibly small number that you probably cannot imagine. Therefore, I thought to put it a bit in scale. If you look at the size of an atom, this is the size of the atom in the same units, and you can see the sensitivity that we have is much better than the size of an atom. And we can go one step further. We can zoom into the atom. We can look at the nucleus or even at the proton. And you can see that even a proton is much larger than our sensitivity. We can actually detect changes in the length of such an arm of less than 1,000th of a part of the diameter of a proton. And the question is, what technologies do you actually need to make this possible? And the numbers that I presented here to you is the achievements of the current detectors, and with the Einstein Telescope, we even want to go an order of magnitude beyond. So you've seen that picture already. These are all the technologies that are needed in order to reach this achievement. Now, I cannot talk to you about all of these technologies in 15 minutes, so I decided to pick out a few, and these are the 4 examples that I picked out, and I want to introduce a little bit to you. Okay, so let's get started. The first one is about vibration isolation. Imagine you have this extremely sensitive interferometer here measuring the distances between mirrors, and then there's a truck rolling by, and with the truck, the surface, the road vibrates a little bit, and it puts the mirrors into vibration, and this will screw up the signal that we're measuring. So in the end, we have to mount the mirrors in such a way that they're isolated from these external vibrations, and the maximum vibration amplitude that we can allow is given here again in this micrometer units. So how do we do it? So here's the idea. We don't bolt the mirrors to the walls. We hang them on tiny strings from the ceiling. And if the ceiling now vibrates, you can see at very low frequencies, the mirror would just move along with the vibration of the ceiling, and it would just move by exactly the same amount. We express this in a quantity that we call the transmissibility, which is the ratio of how much the mirror moves divided by how much the environment moves. And in this low frequency, this is 1. And if you know pendula, you know that there's a resonance frequency somewhere when the pendula is swinging at its natural frequency. And if the vibration reaches that frequency, then it's even the case that the mirror will move more than the environment. Is exactly not what we want. So the transmissibility goes up. But the interesting part is in frequencies which are much above the resonance frequency, the movement of the mirror is much smaller than the movement of the environment. And there we get transmissibilities which go down to a factor of 100 or 1,000 or so. The vibration from the outside is suppressed by factors of 100,000, if you want to push it, maybe 10,000. But unfortunately, you've seen the numbers before, a factor of 1,000 is not enough. So what we could do is we could push the resonance frequency lower, then the isolation becomes a bit better. They can gain maybe another order of magnitude. But the problem is that with lower resonance frequencies, the pendula become longer and longer, and there's a mechanical limit to that. And what we do indeed is we cascade them. So we hang a certain object from the ceiling, and it's damped by this factor, let's say a factor of 1,000. But this is not yet the mirror. We hang the mirror from the already damped object, and we get another factor of 1,000. So now we have an isolation of a factor of 1,000,000. And we can continue doing that. And if we use enough of those stages, we can achieve the necessary isolation from the vibrations of the environment. And here you see how it's done in reality. I hope you can see my mouse. So here the whole system is attached to the ceiling. You can see the first string, and this platform here, this is the first pendulum. And then from this platform, there's another string and a second pendulum and another string and the third pendulum, which is already the shape of the mirror. It's built from glass, and then a fourth pendulum. The mouse, fourth pendulum, and at the bottom, this is now really the mirror, and this gives you enough vibration. This is how it's realized in the LIGO detector. Currently, on the right, you can see a picture. You can see at the bottom, this is the mirror. This is this glass third pendulum This is the platform of the second pendulum, and the platform of the first one is out of the picture at the top. All these things, objects, are just hanging from a tiny thin string, and the structure that you see here around the object, this is just a safety protection in case one of those strings will break to catch the mirror, the expensive mirror, and not having it fall to the ground. Okay, so this is one of the technologies. You can imagine there's a lot of mechanical, challenging mechanics in this system that needs to be developed. The second example I want to talk about is lasers. In the current detectors, we use lasers of 1064 nanometers, but for various reasons, for the Einstein telescope, to make it more sensitive, especially at low frequencies, we want to go to longer wavelengths. As we want to move into the infrared region. Our default for the low frequency interferometer is 1500 nanometers, but we're trying to go even further, maybe to 2000 nanometers. Now, and these frequencies, we don't have lasers yet. These are powerful lasers, but the real challenging part about these lasers is not so much the power, it's the stability. So we have to develop new lasers. And then there's another problem that at these infrared frequencies, silica is no longer a suited material for the mirrors. So we have to also change the materials of the mirrors. And this then kind of creates a whole cascade of new developments that have to take place for those new infrared frequencies. Our default material for the bulk material of the optics is silicon, or if this doesn't work, there would be sapphire, which is currently used at a similar interferometer, which has just gone into an operation in Japan. It's called Kagra. So we have to do, so the problem is that not only the lasers need to be developed, but there are no mirrors, there are all the optical devices that are needed. So a whole system of optics needs to be developed. And here you've seen this picture before. This is for this is now not the bulk material for a mirror, a real mirror, which has just arrived, but not for the Einstein telescope. This is for the ET Pathfinder, so it's somewhat smaller than the ones we will need for the Einstein telescope. Okay, so I guess you can imagine this whole new wavelength has a certain number of other applications. You can maybe think about laser surgery, where the high absorption of those wavelengths in the tissue of the patient is very interesting and could lead to improvements there. Or the same property, the high absorption in plasmas, is interesting for the generation of extreme ultraviolet light, for example, for the silicon industry. My third topic is very much at my heart, because that's what I'm personally working on. It's the vacuum system. Here is a breakdown of the cost of the Einstein telescope. Stefan already mentioned it, and you can see that the two largest fractions of the cost is the tunnel and the vacuum system at almost 600 million euros. So there's a large potential in savings in the vacuum system if we can find cheaper ways of producing vacuum chambers, vacuum pipes, if we can simplify the production, if we can ease the bake-out system for the ultra-high vacuum. And there's also potential to improve the vacuum if we manage to reduce the outgassing of the materials. And then there's another interesting idea whether instead of putting additional diagnostics on the site, whether we can maybe integrate the diagnostics into the vacuum enclosures. And here is a first step in that direction. It's the first composite ultra-high vacuum pipe ever produced by the Fraunhofer Institute IPT here in Aachen. And we're testing it here in my laboratory. And it's made from glass fibers, from epoxy reinforced with glass fibers as an outer structure that gives the pipe the strength to withstand the surrounding pressure. And in the inside, there's a very thin steel liner, which provides a reasonable surface for the ultra-high vacuum. Okay, the last topic I wanted to talk about is about controls, but I have to explain a little bit physics to you before that. At low frequencies, the ultimate limitation of the sensitivity comes from the so-called Newtonian noise. Imagine you have that interferometer sitting there underground in the rock, and a seismic wave passes by the interferometer. A seismic bulk wave, I should say. So bulk waves means that the rock is compressed in certain areas and decompressed in other areas, and this compression moves along with the speed of sound passing by the mirror. Now, the compressed area has a slightly higher density, and from that compressed area, there's a slightly higher gravitational force going to the mirror than from the decompressed area. And if those compressed areas now move, it means that there's a periodic force, gravitational force, acting on the mirror that starts to shake the mirror. And this looks like a gravitational wave and limits our sensitivities at low frequencies. However, there's one single difference between that Newtonian action of a seismic wave and the real gravitational wave, and it's their speed. The gravitational wave moves at the speed of light, and the seismic waves moves at the speed of sound. So what we're trying to do is we're trying to put a whole array of seismometers around the mirror, 3D, at distances of, we don't know yet exactly, hundreds of meters, maybe a few kilometers away, to capture the seismic wave. If we can measure the seismic wave, we can reconstruct the wave field, then we can also reconstruct the action of the seismic wave on the mirror, and we can correct for that. So we can either try to do that in real time by counteracting the movement of the seismic wave. This would be the ideal solution, or we can try to correct for it offline. We will need real-time algorithms that must be essentially based on artificial intelligence, and we might have to run them on FPGAs, which has been done before, but only a few times and not with such big and complicated networks. Okay, thank you. Let me point you once more to the technology catalog if you want to look. Thank you for your attention.
Thanks a lot, Achim.
Yeah, thank you very much, Achim. Do we have first questions, possibly?
Yes, please.
Okay.
Okay. I'm a physicist, and I'm wondering, why are you going to longer laser wavelengths? You would expect shorter wavelength would give you at a given distance a more phase shift.
Yes, that's correct. That's the first thing you think about. The shorter the wavelength, the larger is the change in phase per millimeter. But what is actually limiting the Einstein telescope is not the change in intensity on the outside. This is always detectable. It's the noise that overlays that. And one problem is the so-called shot noise of the laser. At a given power, you have a certain number of photons in each beam, and that fluctuates. And that gives the limitation at higher frequencies. If you now go to longer wavelengths, with the same power, you have more photons and therefore less shockwave.
Okay.
And the power is limited because if you go up too much in power, then we heat the mirrors too much. And then we start to run into problems with the thermal noise of the mirrors. And this combination, if you go through all this, you will find out that it's better to go to longer wavelengths against the initial intuition.
Okay, thank you. If allowed, I would have a second question.
Okay.
Okay. If you look on electromagnetic waves, you have detectors for certain wavelengths. How is about gravitational waves? Do you need several gravitational spectrometer for separate wavelengths of gravitational waves?
That's a very good question. The answer is yes. So depending, different sources produce gravitational waves at different wavelengths. And the sources that the Einstein telescope is sensitive to are stellar sources. So any sources in the size of, in the weight of the sun, up to, we can go to 1,000 times the mass of the sun, maybe 10,000. If you go to even heavier objects, then the wavelength becomes longer and longer. It becomes longer than the arm, and then you've lost the sensitivity, for example. the frequencies go down. This is also a problem on Earth. So if you want to see not stellar object, but if you want to see galaxies, also galaxies produce gravitational waves, then you're talking about masses of 100 million, 100 million, a billion solar masses. And this creates long wavelengths which are outside the range of the Einstein Telescope. It is not possible to detect these waves on Earth because the ground is shaking too much. For example, from the surf of the oceans on the coasts, something you can see anywhere on the continent. So the only possibility to catch the long wavelengths is to build an interferometer which is hundreds of kilometers arm length in space. And there is a second project which is called LISA, which is a space interferometer which is projected, and if it works, will fly in space. It's also a triangular configuration with arm length of million kilometers, and that would be able to see then objects starting from 1 million solar masses up to hundreds of thousands of million solar masses. And there are some ideas on how we could close the gap in between, but those are just ideas. These are not real projects yet. So yes, you're right. Earthbound detectors detect stellar objects, 1 to 1,000 solar masses. With space-based interferometers, we can detect galactic objects with masses of 1 million up to 1,000, up to 1 billion solar masses.
If allow the third question.
Yeah, okay.
Okay. Is there a second use for such a very complex, expensive environment? For instance, I'm thinking for maybe measuring the rotation speed of the Earth with a better and higher accuracy to improve the GPS accuracy.
Nothing on the scale that would justify an investment of €1 billion. So there are some spin-off measurements that you can do, mostly in geology, not so much in astronomy. Interesting things you can do underground, but none of that would justify a €1 billion investment. You could get the same measurement with a much cheaper installation. So the real budget of the Einstein Telescope is justified by the scientific perspectives of the project, and then of course of the technology development and the technology transfers, of course.
Thank you.
Okay. And now there's a question in the chat. I think it's more towards Annick and Ralf possibly. Are you currently working with startup businesses? And if so, what percentage did you contribute? Did they contribute, and to where and to where you are now? And what do you think will be the percentage in future?
Well, of course, our project ET2SMEs is also open for startups. We would welcome if they contribute. As this is the kickoff for the project, well, we cannot give you any percentages at that stage. But in general, when we talk about involvement, when we talk about participation also in voucher projects, why shouldn't startups, if they have a good idea and if they have something to contribute, they could also be, of course, an applicant in that case. No question.
Okay, so Annick, you raised your hand.
Yes, I just wanted to say that Roy Lenders also did another remark. He says for artificial intelligence stuff, you can contact us. So it's Genzai, the company.
Yeah,
so maybe I can give you a few minutes if you want.
Yeah, okay. Yeah, we're working already with NICHEF, University of Utrecht and the Open University for another mid-site thing. and that's starting in June. That's a 2-year project to actually build an AI pipeline, so artificial intelligence pipeline for analyzing the signals coming out of the 3 detectors, but also the Einstein Telescope in the future.
Okay.
So that's on a different scope of the Einstein Telescope. But since the University of Utrecht, Open University, they are also heavily involved in that. They're already building up this artificial intelligence knowledge as well. So I presume you can also use it for the instrumentation part as well, I presume.
Yeah, we should stay in contact. There is a big call from the science ministry in Germany coming up on artificial intelligence in basic research. And I'm planning to apply there, and I would certainly be happy to have a few more partners. So we'll talk offline.
Yeah, okay.
Certainly interesting.
Okay, and I wanted to ask you, did you already register to the Industrial Advisory Board? Roy?
No. What is that?
What is that? That's a place to be.
I didn't even know about that.
Yeah, come on, that's the place to be now, huh? You cannot miss it. No, now you go on the ETS website and you just register, because it's very important to have you with us.
Okay,
therefore, when Annick gets you, you won't get out again.
Okay, I'll register on the website. Yep.
Okay, and then Paul Welling has a question, but he cannot raise his hand. So now you can ask a question, please.
Okay. Hello, I'm Paul Welling. I'm a technician. I see that you're going to work with a lot of mirrors, lenses, all highly specified equipment. My question is, how are you going to keep that clean, and especially not to airborne particles, but to particle deposition, because that can be very noisy to the equipment you're going to make. Companies like ASML or ESA-Aztec, they know what it is to have problems with particle deposition. So my question is here, how are you going to keep it clean, and how are you going to measure it?
Yeah, that's a challenge, and it's something that is very hard to test upfront before you have the real instrument. All the equipment will be produced in clean rooms, obviously, and once it's installed, it will be under ultra-high vacuum. So for various reasons, the lasers over 10 kilometers cannot go through air. They have to be in vacuum, and it actually has to be ultra-high vacuum, 10 to minus 10 millibars. And then, of course, there's no more dust there. So the stuff we're more worried about is that from the cleaning of the vacuum system, there might be some hydrocarbons left on the surfaces which dissolve once we start pumping. And there's a certain risk that we didn't do the cleaning well enough of the vacuum system before we put the mirrors in, and that surfaces are polluted by the remaining hydrocarbons. The dust actually is not our biggest worry because of the ultra-high vacuum. That should protect us from any remaining dust particles. But the specifications on the outgassing on the hydrocarbons is quite stringent. We want to push it to turn to minus 13, 10 to minus 14 millibars of partial pressure in there.
That's correct about the outgassing, but when you look to companies like ASML who are producing in the IUV, they also have problems when they have very small particles in the ultra-high vacuum. So you will have the same problem when you have those dust, those particles in your ultra-high vacuum, and especially when you introduce them by yourself or by the equipment you're going to put in it. So in that stage, in front of it, how are you going to check that everything is clean and that you don't get dust in it?
I'm not 100% familiar with the silicon production technologies, but I don't think that's under ultra-high vacuum. This is a substantially higher pressure what they use, I think. I mean, I'm not, maybe I'm wrong, I'm not familiar. So from our experience from the currently running telescopes, which have a 10 to minus 10 vacuum, is that dust particles are not a problem. So, I mean, we have this experience which shows that this
okay, thank you.
Not our biggest issue.
That was enough for me, so My question is answered then. Okay, thank you.
Okay, thank you very much. Are there further questions? If not, I think this is not a problem. If you have questions afterwards, you can contact us any time. And again, the comment from Annick in the chat, don't hesitate to register to the Industrial Advisory Board. The next meeting will be organized at the end, in the last quarter of this year.
Yes, indeed. I've been waiting a little bit because I think that if we postpone it, there might be a chance to organize it physically. So initially, at the last advisory board, I said it would be organized in June, but thinking about it and with the start of this project, I think it's much better. We postpone it a little bit, we give us the chance maybe to meet each other. And also we will have progressed with the ET2SME project, and we will have a lot of more things to offer and concrete things, and also a concrete voucher scheme to propose to the companies. So I think it's wise.
What I would also like to add is that you, of course, can get into contact with us via the online survey. So each company who will register there, who will contribute, we will come back to the companies, and we will also have the opportunity to have one-to-one talks, maybe to look a little bit more in depth in your specific business situation, and maybe also more specific in your ideas that you have for collaboration. So this is also a very good opportunity. And of course, you can contact us directly if you have any questions.
And for the mapping, if you just visit our website, even in the slider at the very start, you can find the link to the questionnaire. So I think
it's very easy.
Not so hard to find, and as you've seen, and as you have seen in the presentations earlier, we will showcase every company at the mapping as soon as we have got enough companies, or I think within the next weeks, we will start with publishing the mapping. So I think another benefit will be that you will be represented, you and your company will be shown on this map and also on this 3D model of the Einstein Telescope, so that we hope that we can support you in finding the right partners, cross-border partners for innovation projects within ET2SMEs. So I think, yes, joining this questionnaire could be a benefit. Yes.
Yeah, it will be a benefit because it's really, I think so, positioning you as a internationally as a partner in the ET project, and it's positioning you in the right technology. And so there are many ways for companies to collaborate with us, you know, through the procurement, through the vouchers, with the advisory board, with the survey. We can now offer you many ways of collaboration.
Okay. So, and as there are still no more questions, I would say thank you very much for your attendance, and I hope I will see you all soon in innovation projects. Yes, and have a nice afternoon. And now I think Ralf and Annick, what do you want to say?
Thank you, merci. Dankeschön.
From my side, a very big thank you, and please come back to us. Stay in contact with us.
Yes.
Perfect.
Bye bye.
Thank you. Bye bye.
Thanks a lot to all of you.
All right, so let's start. Hello, everybody. So my name is Frédéric Nguyen. I work at the University of Liège in the Department of Urban and Environmental Engineering, which basically forms students in geological engineering, civil engineering, and architecture engineering. And I'm also part of the e-test project, where I lead the also the subsurface part. So I was asked to make a few presentation on different technology that could be developed within the Einstein Telescope, project. And so we gathered with our colleagues from the e-test project, and we came up with a few examples of technology that could be targeted within this ET2SME project. But you really have to take this, I would say, as a starting point. So it's not, what we listed is definitely not exhaustive. There are certainly things we didn't think about, and so that's why we actually would expect also inputs, I would say, from your side, from the companies, as well as to try to foster the activities in that regard. Just as a short reminder, the geological setup, because it's often relevant to develop geological related technology and civil engineering related technology. So the EMR region is basically characterized by a geology where you have first layers in the top subsurface, which are known to be softer, mechanically speaking, so that they're basically allowed to dampen vibration that you might get, for example, from wind turbines, from railways, or from highways, or from industry, for examples, in order to have a more quiet environment at depth, where we hope that we meet basically Flammarian sandstones, so harder rocks where we can install the Einstein Telescope, and in particular we target the solid rocks for the caverns area, so for the corners of the triangle, which will be in the schematic located here. We also know that in the area we have different type of fault systems, and also we have potential karstic dissolution, not everywhere, so we target area where we avoid those karstic dissolution, because it would be an issue for the construction. So the examples that we first thought of and started this technology catalog for is basically I would say organized in 4 systems. And again, I said that it's not this is definitely not an exhaustive or a full list. So we thought first about all the imaging technology that one could develop in order to basically lower the uncertainties on the condition of the subsurface. You also have the tunneling technologies, basically to improve also tunnel drillings, uncertainty related to tunnel drillings, and issue you might get with, for example, water inflow or stabilities. And then there's a part related to simulation and modeling. In particular, we're thinking of the geomodels together linked with the building information models, where we now see in the industry that there's a closing gap in between people who did, let's say, modeling the geology in 3D and then the civil engineering doing the infrastructure modeling in the subsurface, so to make sure that they communicate. And then there's a fourth part, which is related to the water technology, since groundwater is often a major issue when doing underground works. So the first one, as I said, is about geophysical imaging. So that is, I would say, more my expertise. So different technology exists out there. One of the most recent ones that was developed, I would say, in the past year is the image that you see here on the left, to passive seismic survey. So using the ambient vibrations, which are always present in the subsurface, and the sources generated, either the natural sources like the tides, or the anthropogenic sources, to basically illuminate the subsurface and try to build up images of the subsurface, so structural images, so limits between the layers, but also to quantify their properties in terms of, in this case, seismic velocities or attenuation, since this is going to be a big part of this particular instrument, which will be installed at depth. So seismic imaging is certainly going to be a key here. And so within the e-test, we have the seismic reflection lines, which are planned, and also some passive imaging, which are also planned. And next possibility for development, and this is the image on the right, so it might be not so clear from the image, but the idea here is to look at electrical properties of the subsurface as a function of frequency. So you can view the rock as having a conductive part and a capacitive part. And if you combine those two information, and if you scan a piece of rock at different frequency, you're able to reconstruct a spectra, which is shown you here. And you can then correlate some elements of the spectra to some rock textures or to the hydraulic permeability, for example. So this is done quite often in research, not so much, I would say, in the industry at this stage. So there would be a need to try to then be able not only to quantify, for example, hydraulic parameter using local sampling, like a borehole and then pumping test, but also to do it with a larger spatial coverage. So using basically non-invasive imaging to try to quantify some parameters in addition, I would say, to imaging the structures. So that was the first set on the imaging. A second part on the is definitely going to be one on the tunneling, and there's probably a lot of that you can think about here, particularly if you consider the tunnel boring machines, like it's shown you here on the right, where you have advances that can be expected in order to try to predict what type of rock mass condition you might find ahead of the tunneling front, using different type of sensors and drillings ahead of tunnelings, and making use of this data to try to predict the rock mass condition, for example, using machine learning algorithm. Using this data also to perform real-time steering and automation of the TBM, and most importantly, to prevent any difficulties, for example, to prevent being stuck or to prevent some water inflows, and accounting for geotechnical uncertainties as well. So together with that, you also have all the technology that is going to be related to the lining behind the TBM, in particular the ones, because the Einstein Telescope will, of course, need an extremely watertight tunnel in order to operate. So that's one of the issues they had in Japan, is that some water inflow cause issues in terms of disturbing basically the measurements. So the second part is of technology that can be expected as related to tunneling and related areas. A third part, as I said, is related to all simulation and modeling. So what I mean by that is, on one hand, you have the 3D models where you have a lot of software development. So this is an example of the software that we developed in Aachen. It's an open source software that basically built up based on borehole data. You have here different boreholes that are placed where basically you have geological logging information, interface, position at depth. You can also have geophysical properties associated to that, or any type of properties actually associated to that. And from this type of model, trying to do as automatically as possible, but of course there's a huge input in terms of interpretation, to then provide a comprehensive 3D numerical model of the geology. And here we see, for example, the interpolation between the borehole that give birth to the different interface layers and the presence of the faults. And this could be then linked with all the interface, with all the infrastructure. So the so-called BIM, so the building information modeling, where you have all the civil engineering system that are produced, but of course there is a strong interaction between what we're going to build in the subsurface and the geology and the geotechnical properties that we can expect. And so we see a lot in areas for development in terms of, for example, real-time updating. So as the TBM would move forward, you could also think of a way of updating your geological model in order to improve it and to lower subsequent costs. And also related to that, once you have those two systems combined, then you can, because the vibration, for example, is going to be so important, it's going to be really important to understand how, for example, the drainage around the borehole, what kind of flow it will induce surrounding the infrastructure, if it's going to create any type of unexpected vibration. So you have also all the simulation tools of different physical processes that can actually goes along with it. So the last part of technology that we thought about was the water technologies, which basically means being able to predict how much water are actually in the porous or the fracture system. So to be able to quantify the water quantity, so we can think about applying the example is shown here from a borehole instrument from Vista Clara in Seattle. Basically the nuclear magnetic resonance to try to quantify beyond the disturbed area of a borehole in a continuous way how much water we have. And in relation to that also, what is the hydraulic permeability of the subsurface? Another important factor will be the flow. So not only how much water it is, but how it behaves. So basically the flow direction, which is a big issue to actually to be able to establish and quantify, and the magnitude of the flow. So this is an example of the finite volume dilution methods when you inject a tracer, for example, in an open boreholes, and you look at how the concentration of this tracer evolves with time, and can be done also in transient condition to try to estimate the magnitude of the magnitude of the flux, but also to try to quantify the different direction, which is a big target. Yeah, so that's it on my side. So I wanted to keep it short, and again saying that this was really a kickoff for this ET2SME project, in order to also gather inputs for potential project that could be funded with the ET2SMEs, but also for other technology that we of course didn't think about that could be advocated. We can think, for example, of low carbon concrete or mild steel developments that could also be used here in the I would say to promote this region as a host for the Einstein Telescope. So thanks a lot for your attention, and I guess the floor is now open to questions and hopefully answers.
So thank you, Frédéric, for this impulse presentation, and you can use whenever you want the chat function. I can read it, and Frédéric can answer, or anybody else can answer if they're interested, and we can start a discussion about it. Or afterwards, you can use your space thing to ask directly questions. So let me read first the first question for all. Is maintainability of the system taking into account in this stage? For instance, procedures for how to replacing big expensive instruments with help of VR? From Peter van Denberg.
So VR was thought about. If you look at the technology, I think it was mentioned in one of those. I forgot how you call it in English, but those sheets of technology that the use of VR indeed could be used for maintenance aspects with respect to the tunneling. So that's also something that could be brought to the other group, I would say, to the instrument group as well. But it's certainly something that would be interesting to look at. So I don't know who said that. That's HIT. Yeah. So I think that would be an interesting aspect given the size of the system.
Then we've got from Sophie from Twaqua a short comment or an introduction introducing Twaqua specialized. Perhaps if you want to say something, a few words to yourself.
Hi, hello, can you hear me?
Yeah.
Yes.
Hello.
Hi, I'm Sophie. I'm the business developer of Twaqua. We are a spin-off from the University of Namur. So we are not part of the Euregio Meuse region, but of course this project is very interesting to us because we are specialized in monitoring of groundwater flows, and which is of course something that will be needed in this very big project. So we are very excited and very interesting information today. So thank you.
Thank you. So we take note of the company. Yeah. And we'll certainly get back to you as there's dedicated, I would say, technology target in that regard.
Are there any other questions somewhere?
So perhaps to Sophie from Twaqua, I guess this would all. I mean, the instrument that you develop requires, I guess, two wells, right? One to inject the tracer and one to recover it.
Yes.
Yeah.
But of course, you are from the University of Liège.
Yeah.
I guess you are familiar with the work from Serge Bruyère, who
is he's next door. So yeah.
Single well. We are in contact with him. So
yeah. Okay. Yeah. No, he's my neighbor. So yeah, I know him quite well. Yeah. Thanks a lot.
Okay. Anyone else?
I'm just
someone.
Yeah.
Sorry, Frédéric.
No, I'm curious to see if you thought about other development from the industry side. Of course, it might be difficult to answer on the spot here, but certainly don't take what I said as being closed. It's certainly absolutely not. So the ET2SME is basically aiming to distribute. I mean, to distribute those vouchers that we talked about earlier to further develop, some key technology that will enable the presence of the Einstein Telescope in the region. So I guess that required the two companies, right, from Dirk from across the border, and yeah.
So perhaps Frédéric has presented the technologies which we want to address within the project, on which will be needed for the Einstein Telescope. I think there are different companies here in this session also. We've got a chance now to give a short introduction to you. If you say, okay, we are working in that field, or we're interested in that field, so we could imagine that we want to participate in the voucher scheme, for example, for that. Is there someone who wants to?
Maybe we can do
introduce someone?
Dirk, we can ask people to basically raise their hand. Is there a thing they're going to apply for those vouchers? Because I guess there are also people coming in just for the information, which makes totally sense. But this is different from, because I see some people I know, like Christian or Sebastian. So it's different from other meetings we had where we present the results that we got here. It's really to try to promote the development of technologies. So And it's also much different from the advisory board that we have.
Yeah.
So maybe can we ask you in the audience to perhaps do a reaction, like raise your hand if you are thinking about submitting or considering submitting a voucher for this technology development. Just checking how to do that actually before I ask people.
Two. I think Mr. Telkamp, not one. What is the B for? If you want to start.
Yeah, I have to unmute it a little bit. My name is Ben Telkamp. I'm from the Fulgro company. Well, for us, this is in this stage informative because we have to see what's all possible, and I think there are more than one field where we would be interested in taking part in this scheme. But yeah, we'll have to see, and then we'll have to contact the specialists within your organization to see if there's a possibility.
Yeah. So I guess one key thing to understand is that I mean, if you looked at the timeline that was presented earlier, so we're going to have a first feedback on the S3 proposal this June, which already going to set basically the project going, and then the site decision is going to be made. I think it was 2024, right? So until 2024, there is this so-called bid book that we have to make with the region, and there are definitely advantages of building and fostering the technology development in this region compared to Sardinia, for example. Although there are probably different things that I didn't think about it of Sardinia, but the amount of companies that would be able to actually contribute to and grow with the instrument being installed here is certainly a heavy wager, I would say, in our hand. And things that develops like low carbon concrete, for example, that my colleagues do here, are certainly things that we can also promote through the project.
Mm-hmm.
Yeah.
Okay.
Thanks. So maybe we can move to
Peter, I think.
Yeah, Peter
was the second.
Yeah.
Yes. Hello. My name is Peter van den Berg. I'm from Heemskerk Innovative Technology. Yeah. I just asked my question in the chat for the how to proceed or how to do maintenance in the tunnels. I think I joined this part because simulating and modeling was as an item here, so that's why I joined here. So to proceed, do you think it's good to contact the business developer of the simulation and modeling part?
Yeah, certainly. I think this is something that could be certainly considered. Yes.
Mm-hmm. And the third, Ana Maria Alonso Blanco. His name.
Hi.
Hi.
Oh.
Hi. So we're I'm from a company that's called Technologies Online Catalogue. It's a startup that's a spin-off from the RWTH University in Aachen, and we are also the team behind GEMPI.
Oh, okay, great.
Yeah. So yeah, we're also working and doing some developments around GEMPI at the moment, having a visualization platform for different platforms, also like 3D or virtual reality and things like that. So yeah, this might be something that we can work on for this project also.
Yeah, certainly. Okay, great. Nice to meet you.
Mm-hmm.
Nice to meet you too.
Mm-hmm. So anybody else wants to ask a question, wants to give a comment? If not, then it's only to invite you to the next Industry Advisory Board meeting of ETS and ET2SMEs. where we will present the technologies again, and where you can discuss it with all the other partners of the project. And if there's no one else,
yep,
last chance. If not,
thanks again.
Then we have to say, yeah.
I was going to say thanks again for joining us. I actually have an advisory board in another meeting, so I'm going to have to leave at 2:30, which is about now.
Mm-hmm.
Thanks a lot for your presence and for your input, and make sure to keep in mind that this is really a kickoff, and we hope to grow this catalog of technology, in particular for civil engineering, infrastructure, and geological technologies. So thanks again, everybody.
Thank you from the team of the ET2SMEs project, and hope to see you again during our next meetings or workshops or trade fair participations or whatever. So.
Okay. Thank you. Bye-bye.
Have a nice day, rest.
Take care.
Bye-bye.
Bye-bye.
Bye-bye.